Hello everybody, and welcome to the second part of my video about normal distributions and examples, the item you all have waited for, which unfortunately is a two-parter, but that's beside the point. So, excuse me, still coming off my cold. Basic z-scores, the ideal refresher. In this particular case, we're only going to revolve around one particular formula of z-scores, and that is with the population definition. I know you can say z-scores in this way, or you can refer to the finding the value z-score equation, in which case there's nothing wrong with that as long as the z is still in place. But more importantly, you have to have normally distributed data. This normally distributed data is the precursor to all statistics questions, especially if they revolve around z-scores. They have to be normally distributed. You have to be given a mean value, so a mean here or a mean here, doesn't matter which one you use, or a standard, correction, you have to be given a mean and you have to be given a standard deviation. Now, theoretically, an instructor could give you a mean and force you to find the standard deviation by giving you raw data. Most people won't be that cruel. And by cruel, I mean making you actually think about how you're going to get it by either by hand methods from a previous formula or another video which I'm going to post up about how to use the 1var stats function appropriately. But again, besides the point, whole nother day. Just know that this equation here is your love and savior for the entire semester. So, z-scores help you define the following question. Which item is significantly higher, or greater than, whichever terminology you prefer, than the other? So we're going to spit out a couple of random data sets. So I'm going to give you a value of 30 in a distribution where the average is 50 and a standard deviation of 10. But wait a minute. If we pull out a second data set with a data value of 35, the same average, but a different standard deviation. Let's skew this down to 5. Hidden assumptions here. 30 goes to 50, 35 goes to 50. So most people will think 35 is the higher one. Let's check it out. So z-score equation, 30 minus 50 divided by 10. And we have a z-score equation of 35 minus 50 divided by 5. Let me just catch up to myself here. Here we go, and the 5. Now, we do all the math accordingly. We get a z-score of -2, and we get a z-score over here of -3. So which one's significantly higher? Got news for you. It's not the 35. It's actually the 30. And the whole reason why that people will get this wrong on the first shot is they'll only look at those two particular values, the data value and the mean, data value and the mean. These don't mean jack diddly unless you know what the standard deviation is. So any question that you have in statistics revolving around z-scores, look for that standard deviation. Now many people could say, no, -3 is higher than -2. Let's draw a basic number line just to make sure you guys understand what exactly it is we're doing. But we're going to attach that number line underneath a normal curve or a bell-shaped curve. So this is a z-curve, and in the center of every z-curve is 0. So if we were to map out our terms accordingly, we got a -3 and we had a -2. -2 is still closer to 0. Therefore, that is the winner. So if somebody asks you what's significantly higher and you're given two values, just like in the previous slide, and you do all the math for it, haha, z-score, -2 versus -3, winner. And if you don't truly understand why we converted to z-scores, we didn't just look at the distribution, please refer to my previous video about why we use z-scores as a standard. So, what is the likelihood of an event? What are the most common questions that you'll ever get stuck with? And we want to make sure we understand notation. Now, teachers often give out this notation in terms of probability statements. So, probability of something less than a number, probability of something greater than a number, or probability of a number less than the event, me just catch up to myself here. Less than the event, which is less than another number. Notice how I'm sounding very monotonic here because I see these over and over and over. But more importantly, this one's a little funky, but we're going to give these all clever names in just a minute. So don't worry about how these look at the moment. We're going to actually give you graphical representations of all these. So now that you got your 4 items, the one on the top left we'll refer to as a lefty system. Notice how the arrow is pointing to the left. We got the righties, which are pointing to the right. We got the tweeners, which X is in the middle. And we have your split systems, mostly because there's that or in the middle, but we'll explain that in a minute. The lefties always involve something going less than. The righties are always involving something going greater than. The tweeners, X has to be in the middle. And in the splits, usually have a less than or greater than situation occurring. Now keep in mind here, X is a variable. It could be the likelihood of seeing more than 30 people graduate from college. It could be the likelihood of getting to a certain GPA, etc., etc. But X is not the number you're solving for here. It is the likelihood of that number occurring. Each of these number symbols, these will be given to you. All right, still with me? Awesome. So, if I had to give you visual representations of each of the items I just demonstrated to you, a lefty underneath a normal curve here. Come on, I'm going to try and make these look good today. And nailed it. So, given that you have your center, a lefty usually revolves around some z-score. And if you had to show this graphically, it would be the likelihood to less than that z-score. So in interval notation, which you should have learned in previous courses, you go on from negative infinity up to z. Now, if I had to do a righty on the other hand, and again, you're going to try and nail this, and we got it. So once again, righty scenario, you got your center of the distribution, and again, just any random point going off into the right, interval notation, some z-score going off to positive infinity. This is not a difficult concept, but once you get the interval notation down, as long as you see whatever statement you have, you're set. Now a tweener, it's always in between two values. And if you know what a confidence interval is, you've been doing tweeners for a while now. But in a tweener, you're not going to use the infinities to your advantage. You actually have to work with two different values. And an interval notation is the lowest value to the highest value. Now the splits, I'm not going to draw a representation for this one because what you're really dealing with is a lefty and a righty at the same time added together. So when you're doing this particular piece, you have to do two separate equations. In the next video, we're actually going to do two separate equations from each of these particular systems. So we're going to do two lefties, two righties, two tweeners, and two splits. Simple enough? Everybody okay? Get ready for the next video.